Good morning, students. सार्थक आवाज येते का? यश.
येतोय सर.
Okay. Screen is visible. Yes, tell me the screen is visible or not. Anyone?
Visible sir.
Okay. So in yesterday's lecture, we discuss about the unit cells. What is meant by unit cell? So this unit cell is important for the examination point of view because examiner can ask the definition. What is meant by unit cell? So remember, it is the smallest repeating unit of the crystalline solid. Each crystalline solid is made up with unit cells. Yesterday also we seen these examples of cubic unit cell. See, this is an example of cubic unit cell. See in this diagram, this red colored portion is the unit cell. These are the lattice points. So many unit cells combined together and a big crystal is formed. In this lower diagram, we can see the parameters of the cubic unit cell. I am talking about the cubic unit cells. There are different 7 crystal systems are there. So out of these 7 crystal systems, we here taken the example of cubic unit cell. So each unit cell having the edge lengths. See, you can see this is edge length C, this is edge length A, and this is edge length B. Yesterday also we seen this edge length differs in a different crystal structure, but in case of cubic crystal structure, this A is equal to B and B is equal to also C, and these are the angles alpha, beta, gamma. So depending upon this edge lengths and angles, there are 14 Bravais lattices and 7 crystal systems. This part is also, I explained yesterday, the types of unit cells. So one is primitive, means all the particles are at the corners. Then body-centered unit cell, in which along with the particles at the corners, there is one particle at the center of the body. Then face-centered unit cell, in which along with the particles at the corners, at the center of each face, we can see clearly at the center of each face, there is a one particle. And last one is a base or end centered unit cell, in which any two opposite faces, at the center of any two opposite faces, there is a particle along with the corner particles. So these are the 4 types of unit cells. Then there are the 14 Bravais lattices, and 14 Bravais lattices are divided in 7 crystals. So these are the 7 crystals. Also, I have given the idea how to remember this 7 primitive unit cells. Make a practice of these unit cells, because for the competitive examinations, the question can be asked in which unit cell the angle is alpha beta is equal to 90 or gamma is equal to 120. So we have to remember these angles for the competitive examination. For board examination, these values are not expected. Then we are considering particularly cubic unit system. So this cubic unit, in this cubic unit system, there are three kinds of unit cells. First one is simple unit cell. All the particles are at the corner. It is called as simple, or it is also called as primitive unit cell. Then body centered, you know about this body center along with the particles at the corner. One particle, we can see this particle. This is at the center of this body of the cube. That's why it is called as body centered unit cell. Then I'm coming to the face centered cubic unit cell. As the earlier explained, as the center of each face, we can see at the center of each face there are particles along with the particles at the corner. So these are the three types of cubic unit cells. So in this diagram, in this previous diagram, we can see these are the three unit cells of cubic. Then orthorhombic having the all four types of unit cells, end centered also there. This is face centered, this is end centered, this is the body centered, and this is primitive. In case of tetragonal, there are only two types of unit cells. One is simple, this is simple, and one is body centered. So there are 14 different Bravais lattices are there, and the 14 Bravais lattices are divided in seven crystal systems. See, first one is cubic, orthorhombic, tetragonal, monoclinic, rhomboedral, triclinic, and hexagonal. These are the 7 crystal systems. But we can find here 14 different structures are there. 14. See, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So these are the 14 types by which we can join the lattice points. So 14 Bravais lattices are there and 7 crystal systems are there. Now today we will discuss about the number of particles present in cubic unit cells. Already we discussed there are 3 types of cubic unit cells. First one is primitive. In the previous slide, it is shown there are 3 types of unit cells: primitive, body centered, and this is a face centered cubic unit cell. Now what we have to do, we have to find the particles. We have to find the particles, number of particles in the cubic unit cell. First we will consider the primitive or simple cubic unit cell. See this diagram number, there are 3 diagrams. It is shown A, B, C. In the A diagram, it is open structure. This is a B diagram. This is space filling structures, means actually the spheres are shown. And this is a C structure in which actual portion of the particle, means actual such this portion of the particle is belonging to the 1 unit cell, means 1 unit cell contains this much portion. It is shown with figure number C. In this diagram we can see there are 8 unit cells: 1, 2, 3, 4, 5, 6, and 7, and 8. So these 8 unit cells in a simple, these are the simple cubic unit cell. So each corner particle is shared between 8 unit cells. Means after combining these 8 unit cell, we will find this one particle will be prepared. One particle will be prepared. So how this one particle will be prepared, this is explained here. Simple cubic unit cells having the particles at its 8 corners. We can see here 8 corners, means the particles are there at the 8 corners. When these unit cells are stacked together, when stacks together, or it is also called as combined together, when these unit cells combine together, the particle at each corner of the given unit cell sorry, the particle at each corner of the unit cell, each shared with 7 other neighboring cubes. We can see here. Means if you consider this small corner, this particle is shared with another 7 cubes. We can see here 1, 2, 3, 4, 5, 6, 7. So by this diagram, it is picture is actually, yes. By this diagram, we can understand means one particle is shared between 8 different cubes. 8 different cubes. So the corner particle contributes its 1/8 part only, 1/8 part. So in this C diagram, clearly we can see the actual portion belonging to the unit cell. So as there are, see, we can see here 1, 2, 3, 4, 5, 6, 7, 8. So 1/8 into 8 is equal to 1 particle, means there is only 1 particle is present at the in primitive or simple cubic unit cell. Only 1 particle is present, and this 1 particle, how it is prepared? By joining 8 different cubes. Means when 8 different cubes join together, we will get 1 particle. This 1 particle. So I think it is clear. It will be not asked for the examination purpose, but it is required for the solving the numerical. So remember this thing only. 1 particle is present in primitive or simple cubic unit cell. And how this is prepared? Means each unit cell only having 1/8 part. 1/8 part. So this 1/8 part of the given unit cell. Then I am coming to the body-centered cubic unit cells. As you know, at the center of this body, there is a 1 particle, and these 8 particles. So 1/8 into 8, it is equal to 1 particle plus 1 particle. This is at the center of the body. So there are total 2 particles present in the body-centered cubic unit cells. In case of primitive unit cells, there is a 1 particle. In case of body-centered unit cell, there are 2 particles. See how these particles are prepared. So at the corners, 1/8 into 8 is equal to 1 plus 1. This plus 1 particle, it is present at the center of the body of that unit cell. So there are 2 particles. We can see this is open structure. This is a space filling structure, and this is actual part. This is the same diagram as previous diagram. This is actual portion of the particle belonging to the body centered cubic. You can see clearly at the center of the body there is 1 particle, and 1/8 particle into 8 is equal to 1. Then I am coming to the face centered cubic unit cell. Now here also the 8 particles are present at the corner. So 1/8 into 8 is equal to 1. We can see here 1/8 into 8. So first particle is already present. Then in case of face centered unit cell, we can find here at the center of each face there is 1 particle. But this 1 particle, actually the half part is shared. We can see here in the C diagram. It is a printing mistake. It is actually C diagram. In the C diagram, clearly we can see this half part means each particle at the center, each cube having the 6 faces. So we can see clearly here the half part is shared with another cube. So as there are 6 faces, 6 into 1/2. Why 1/2? Because each particle is shared between 2 unit cells. So 6 into 1/2, it becomes 3 particles. So this 3 plus 1 total is equal to 4 particles. So the number of particles in simple cubic unit cell, there is only one particle. Then in case of body centered unit cell, there are 2 particles. And in case of face centered unit cell, there are 4 particles. So these values are required for solving the numericals. There will be no question on this drawing the diagrams or how the particles can be calculated. So remember these values only. Don't remember these structures. These structures are given for the understanding purpose. For the understanding purpose, these structures are given. Only these values are required for us. Now, there is a relation between molar mass, density of a substance, and age length of the unit cells. Now you are familiar with the age length. See, once again, I'm explaining what is meant by age length. Age length, it is shown in unit cell. See, this is A. This A, B, and C. These are the age lengths of the unit cells, and these alpha, beta, gamma, these are the angles. Yes, again I am coming to the relation between molar mass, density of the substance, and age length of the unit cell. Suppose if m, small m, is the mass of one particle. Remember, if small m is the mass of one particle, I am talking about only one particle, not the unit cell. If small m is the mass of only one particle and small n is the number of particles per unit cell. So these number of particles, now we are familiar with these number of particles in unit cell. In case of simple cubic unit cell, there is only one particle. In case of body centered unit cell, there are 2 particles. And in case of face centered unit cell, face centered cubic unit cell, we are only considering the cubic unit cells. For your syllabus, only there are 3 cubic unit cells. One is simple, second one is body centered, and third one is face centered cubic unit cells. We are considering only cubic structure. We are not considering the rhombohedral, octahedral, tetragonal structure. This is not for your syllabus. Only we are considering the cubic unit cells. So small n is the number of particles in unit cell. M is the mass of one particle. Small a is the age length of the unit cell. In case of cubic unit cells, A is equal to B and also the B is equal to C. All the age lengths are same. So the mass can be given, mass of the unit cell. Now mass of the unit cell is equal to M into N, that is mass of one particle and multiplied by number of particles in the unit cell. So volume of the unit cell will be A cube, that is the age length cube. Volume, it is given A cube. So density is equal to mass upon volume. So the formula of the density is denoted with this symbol rho. Rho is equal to this mass upon volume. So the value of mass m into n divided by A cube. This is the density. So density is equal to mass upon volume. We will get this equation. But m is the molar mass. If capital M is the molar mass and Na, capital N and small a, it is the number of particles per mole. Number of particles per mole, it is also the Avogadro's number. You are very familiar with this Avogadro's number. So Na, this Na is nothing but Avogadro's number. It is also called as the number of particles per mole. So molar mass is equal to mass into number of particles. The same equation it is written here, m into n, where this Na is the number of particles per mole. So small m is equal to m divided by Na. This is the mathematical steps. M is equal to molar mass divided by Na. So we can put this value, mass is equal to m divided by Na. In this above equation, we can put this value here. So density is equal to n into m. N is already there, and m means this. This value of m we are going to put in this equation. So n into this capital M divided by Na into a cube. So by using this formula, we can calculate the density. If this n is known, number of particles are known, age length is known, already this Na value is available, and if this molar mass is known. So for the board examination, the question will be there, the numerical will be there on this. Calculate the density. We will see the one numerical. If you understand this relationship between density, rho is density, where small n is the number of particles per unit cell, m is the molar mass, a this is age length, and Na means it is Avogadro's number, that is number of particles per mole. So one numerical is given here. So we can solve the numericals, all the students having the notebooks. Yes, anyone tell me you are carrying your notebooks or not?
No.
So, okay. Just see the steps. What are the steps given, and what are the values given? First, read the numerical 2 times. What is the numerical is given when gold crystallizes? Means we are not required what is the gold is given or silver is given or niobium is given or any metal is given. We are not interested in the metal, which metal is given. We are only interested in the whether it is face centered or body centered, or it is a simple primitive. So gold, it is given, it forms a face centered cubic unit cell. So face centered unit cell, immediately we have to remember how many particles are there. 4 particles are there. So face centered unit cell means there are 4 particles, means you got this value n is equal to 4 here. Then the unit cell having the age length 408 picometer, means you got this value of A also, means A is known, n is known. Calculate the density. Density, it is as you having this formula, rho is equal to m into n divided by a cube into n. Now this molar mass, this is also given. Molar mass is also given. Molar mass of gold is 197 grams per mole. So put these values in this equation. M is equal to 197 grams per mole. N is equal to 4 because n is equal to 4 means by using this face centered unit cell we calculated this value. So for this purpose this is given. If it is a body centered cubic unit cell, then n is equal to 2. If it is given simple primitive unit cell, n is equal to 1. So I think you understand from where this value of n comes. These are the number of particles in face centered cubic unit cell. And Avogadro's number is given. See, 6.022 into 10 raised to 23 atoms per mole. So all the values are known by putting these values in this formula. Rho is equal to, so rho is given here, 197. The value of m, it is substituted, grams per mole into 4 atoms. This n is equal to 4. And we have to do this a cube, because a is given in picometers, we have to convert in centimeters. So 408 picometers, it is converted into 10 raised to 12 meters, and 10 raised to 4.08 into 10 raised to minus centimeters. So picometer we have to convert into centimeters. So this is a value of 4.08 into 10 raised to minus 8 cube, because in the formula we have to do the cube, and into this Avogadro's number. So this atom will be cancelled, mole will be cancelled. And after solving this step, if you write this step, you will get 2 marks. Remember, if you write this one, you will get 2 marks. So for doing this calculation, there is 1 mark is reserved. So this is the mathematical part. You can solve this cube by using the log tables and mathematical calculation, how to do the division, how to do the addition and subtraction. Go through the log table and we will get this 19.27 grams per cm cube, or you can write into kilogram per meter cube. You can write in this unit also, you can write in these units also, both the answers are correct. So this is the numerical for 3 marks numerical. This numerical will be asked for 3 marks for the board examination. Now, many numericals are given at the end of this PPT. So you can go through the numericals. Also, some numericals are given in the exercise. That exercise numericals also I have solved. And already these are inserted in this PPT also. So all the numericals are solved. You do not have to solve any numericals. All the numericals I have given at the end of this PPT. So again, we will move to the next part. This next part is very, very important part. This is a packing of particles in the crystal. Packing of particles in the crystal lattice. Packing means maximum how many particles or maximum space utilization. That is called as packing. So before this packing of the particles, you have to understand this, what is mean by coordination number, because this is asked for the examination. Define coordination number. This coordination number is different in that chapter, coordination chemistry. That definition is different here in solid state. The coordination definition of coordination number is different. In this chapter, coordination number means it is the number of neighboring spheres that touch to any given sphere. So these are the some squares, spheres. These are arranged in a straight line. Horizontally, these spheres are arranged. Now, if we consider this particular sphere, this sphere touch to this this sphere and this sphere. So coordination number is 2. Coordination number means the neighboring spheres that touch to any given sphere. So this sphere touch to another these 2 spheres. So the coordination number is 2. I think you understand the concept of coordination number. So coordination number means it is nothing but the how many spheres touch to that particular one sphere. So we'll discuss about this closed packed structures. Closed packed structures means maximum space it will be utilized, how the maximum number of particles or maximum number particles can be considered as spheres here. Spheres and particles, sometimes the spheres word is used, sometimes the particle word is used. So we will discuss the first type, closed packing in one dimension. It results by arranging the spheres to touch one another in a row. So this is a one dimension closed pack structure. This is one dimension. Then we are moving towards the closed packing in 2 dimensions. So the 2 dimension structure can be prepared by arranging the rows together such that they are in contact with each other. There are 2 ways. There are 2 ways by which we can arrange the 2 dimension structure. See, this experiment or this packing we can do at your home. Only we have to purchase the plastic small balls. These small balls we can arrange such type, AA type of arrangement. AA type of arrangement, these are the simple balls. Below this, this is a, suppose this is the first layer, this is the second layer, this is the third layer, this is the fourth layer. all the layers are same, all the particles are same. That's why this A type of arrangement is there. So below this first layer, the second layer is kept. Below the second layer, third layer is kept. Below the third layer, fourth layer is kept. Such type of arrangement is called as square close packing. Why this is square close packing? If you consider this particular sphere, this sphere is in contact with another four sphere. We can see 1, 2, 3, 4. That's why the coordination number is 4 here. Coordination number is 4 because we can consider any sphere. If you consider this sphere, this is also contact with this 1, 2, 3. See, 1, 2, 3, and 4. So if you consider any sphere which is in contact with another four spheres, so the coordination number is 4. That's why it is called a square close packing, because square is obtained by joining the four centers of the spheres. This is the center of this first sphere, second sphere, third sphere, and fourth sphere. So we will get here a square. Square is obtained. That's why this packing is called as square close packing, in which the layers are arranged A like this. Now the second one is hexagonal close packing. We can see this diagram. This is a layer. Now the B layer is not kept below. It is kept in the depression. So we can see here the packing is decreased here. We can see here, see this, see the space here, and we can see this, see the space here. So this is the maximum close packing is there in hexagonal close packing. Why this is called as hexagonal close packing? Because we can see here the hexagon is prepared here. Hexagon is obtained and the coordination number is also changed. See, the coordination number means this sphere is contact with 1, 2, 3, 4, 5, 6. So the coordination number is 6 here. And this packing is obtained when the spheres are closely packed. We can see clearly this structure, this packing. In this packing, the spacing is more. So this spacing is decreased in this hexagonal close packing, because if suppose this is a layer number A, the B layer is not kept below exactly. It is kept in the depression of the first row. See, in this depression it is kept. Again there is a layer, again B layer. So this is AB type of arrangement. This is AA type of arrangement. This is AA type of arrangement. This is AB type of arrangement. AB, again AB, again AB. So this is a hexagonal close pack structure, and the coordination number is 6. Why the coordination number 6? Because each pair is in contact with another 6 spheres. I think you understand this hexagonal close packing structure. If you any doubt, then ask me. If any student having the doubts regarding this hexagonal close pack structure, why it is called as hexagonal? Because hexagonal is prepared here, and this is square close packing because the square is obtained here. Coordination number, remember the concept of coordination number means one sphere is in contact with another sphere. This is called as the coordination number. Now, close packing structure in 3 dimensions. We consider here 1 dimension. This is the 2 dimension. Now we will consider the close packing in 3 dimension structure. 3 dimension structure, we can see this is a first layer, then second layer, then again third layer. So this is first layer A. This is again second layer A. Again this is the third layer A. This is the fourth layer A. So this is a 3-dimension square close packing structure. So this arrangement we can do also at your home. We can see this is a type of arrangement. The coordination number is 6 here. So I will explain how the coordination number 6, 4 is, see the coordination number is 4 in the layer 1, 2, 3, 4. So if another layer is above this one, then another layer. So if a type of arrangement is done, the coordination number will be 6. So how it will be 6? Because each pair is in contact with 6 pairs. How? 4 in the layer, 1 is above and 1 is below. So if such type of arrangement is there, also we can do at your home also, but only we have to purchase a box of these spheres. So if you made this arrangement, a type of arrangement, then you will understand each sphere is in contact with 6 pairs. That's why the coordination number is 6. See, the coordination number is 6. It is also explained 4 in its own layer, and 1 is above and 1 is below. So polonium is the only element that crystallizes in simple cubic closed pack structure. Remember, this can be asked for the MCQ. Which is the element that crystallizes in simple cubic closed pack structure? So this polonium is the only element. The possibility, maximum possibility is there to ask the MCQ on it. So remember this polonium. So we consider this is AA type of arrangement. Then there is also possibility of AB type of arrangement. So in this AB type of, but we are considering the 3-dimensional. We consider this is in 2-dimensional. So this is a 2-dimensional AB type of arrangement. In 3-dimensional, what will happen? So in case of 3-dimensional AB type of arrangement, we can see here triangular voids in the first layer are not covered by the spheres of the second layer. See this diagram. This is a 3-dimensional hexagonal closed pack structure. See carefully, because this is very difficult to understand. Tomorrow also I will explain, because only 1.5 minutes is remaining. I will try to explain. So this is the first layer. We can see this is A, this is A, this is A layer, which is shown with black color balls. This is B layer. This is a B layer. It is fitted in the depression of the, see, this is in the depression of the first layer. So this is A, B, A layer is behind, B layer, again A layer, again B layer, AB type of arrangement. So what will happen? There are 2 types of voids are obtained. Voids means these are the empty spaces. See here, if the 3 spheres are in the A layer and 1 sphere in the B layer. So this is a B layer, this is A layer. So we will find this tetrahedral hole. See here, we can see here. This is a tetrahedral hole. This is also tetrahedral hole. This is also the tetrahedral hole. So these tetrahedral holes are prepared when this arrangement is there, 3 and 1. Means 3 spheres of A type, and this is a B type. We will find the tetrahedral holes. And opposite to this, when there are 6 spheres,